In the previous video, we saw that our transfer function equation for this discrete circuit matched the ideal form for our feedback circuitry. And what we're going to look at in this video is our input resistance and output resistance and see if we can't relate that to our ideal form for our feedback circuits. So first, let's start with our input resistance. So I've copied the same small signal circuit that we had in the previous video. And notice I have our input resistance with feedback labeled in purple on the left. So it's looking in from this left side at our input terminals. And so we note that our feedback resistance is equal to our input voltage VI divided by this base current I sub B. So like we had said previously, we can relate our VI to our V pi and our output. So we have VI equals V pi plus V out. And so we can see that by doing a KVL around this loop if we want to. From there we can say that, well, our V pi from Ohm's law is just equal to IB times R pi, and our V out is equal to IE times RE, where I'm going to kind of combine two steps into one. Our emitter current is equal to base current plus collector current. Not sure what just happened there. Let's get rid of that. So our base current plus collector current times our emitter resistor. Okay, so let's take that second term a little further, and we can say our input voltage is equal to IB times R pi. I'm going to leave that alone for now. And then let's say we have IB, but our IC, let's change it to be HFE times IB. So right here, whatever in that second term is still just IB plus IC, and we still want to be multiplying that by our emitter resistor R sub E. So of course now we can factor out the base current from both terms. So we have I sub B times R pi plus the quantity of 1 plus HFE, so remember that is our current gain of the transistor, times our emitter resistor R sub E. Okay, so now our input resistance R sub IF, coming back up here, we said is equal to this input voltage VI divided by IB. So essentially we're just going to be dividing through by IB and taking this out. So we find then that our input resistance, R sub IF, is equal to R pi plus 1 plus HFE times our emitter resistor RE. And so we can sort of rearrange this a little bit. So this is R pi plus 1 plus GM R pi, just by definition of our current gain, times RE. And so let's actually, once we have this, we can then factor out an R pi. So I have R pi times 1 plus the quantity of 1 divided by R pi plus GM times RE. So you're probably thinking at this point, why in the world am I doing this? Well, notice now we have this familiar term here, and so we can use that lowercase r sub e that we had defined previously, and we can say that our R sub IF is equal to R pi times 1 plus RE over lowercase r sub e. And so this follows the same general form where we have that our R sub IF is equal to our input resistance times 1 plus beta V times A sub V. And in this case, by inspection, we have that our input resistance is R pi. As we discussed in the previous video, the beta V is 1. And also, as we saw in the previous video, our A sub V is RE divided by a lowercase re. So again, we see this is the same as our ideal form. Okay, so now let's move on to our output resistance. So we're going to be using this same circuit, but now for output resistance, we want to deactivate our independent sources. In this case, that's our voltage VI. And to deactivate a voltage source, remember we replace it with a short circuit. And after we've done that, we're going to apply this test source. It can be either a voltage or a current source, doesn't really make much difference. Now we're going to be looking at the resistance, looking into the output of the circuit, which as you can see over here is going to be equal to Vx divided by Ix, where that is the test voltage and the test current respectively. So we're going to start by doing a Kcl equation. So from Kcl, we can say sum of the currents in, which is going to be at the top node. Coming in, we have Ix and GmV pi equals the sum of the currents out, which we have Vx divided by our emitter resistance R sub E plus Vx divided by our R sub pi. Well, we can sort of rearrange this to, we want to ultimately have this goal of getting Vx and Ix, so let's start by getting our Ix just on this side, and that's equal to Vx divided by Re plus Vx divided by R pi minus our GmV pi. Well, we want to get rid of this V pi, and ideally we want to get it in terms of Vx, and we can do that quite easily by doing a Kcl. In this case, we don't have the V in anymore, so we just have these two voltages. So doing that KVL, we can see that our V pi is equal to negative Vx. So if we substitute that in, we're going to have Ix is equal to Vx times 1 over Re plus the quantity of 1 over R pi plus Gm. Sorry, let me do parentheses, brackets, okay. And so again, you'll notice I've kind of grouped these terms maybe a little awkwardly at first, but we'll note again this can be used to relate back to that lowercase r sub e that we had defined previously. So we can say this is actually equal to Vx times 1 over our emitter resistor plus 1 divided by our lowercase r sub e. All right, so now we want to find that output resistance. So our output resistance is equal to Vx divided by Ix. So we just take that previous equation, divide our Ix to the other side, then we have to divide that quantity in the brackets to the other side. So we're going to have 1 divided by r sub e plus 1 divided by lowercase r sub e inverted. And we note that this is the same as saying we have our two resistor values in parallel. So our emitter resistor in parallel with our lowercase r sub e. And so another way that we can write that is, this is our output resistance, is equal to, our special case for two resistors is capital R sub e, lowercase r sub e divided by the sum of the two. Sorry, not sure what's going on there. So the sum of the two, so we get something that looks like that. Okay, so now playing some games to kind of get it more familiar in terms of the form of our ideal. Let's divide both our numerator and the denominator by r sub e. So I'm going to divide both of these by 1 over r sub e, and so of course this term in the brackets here is just a special form of 1, so it's not changing the relationship. And so what we see then is that we have r sub e divided by 1 plus r sub e, our emitter resistance, divided by lowercase r sub e. So we get something that looks like this. And so recall, we know from previously that our beta sub b is 1, and our a sub b is equal to Re, try again there, is equal to r sub e divided by that lowercase r sub e. And from inspection then, we can see that our output resistance without the feedback is equal to our emitter resistor. And so this then is going to match our ideal form. So this matches ideal form, which as you recall is that this output resistance with feedback is equal to our initial output resistance divided by 1 plus beta v AV for our voltage amplifier. So again, with our input and output resistance, just like we saw with our transfer function, these forms can be made to match our ideal forms if we can find the right relationships for our circuit parameters.